Hello students, today we'll look into more of entropy. So far we have seen what is entropy as a function of state and define a second law of thermodynamics, from which we have seen Carnot cycle as the most efficient engine, and an equivalence has been made between absolute temperature and ideal gas temperature. And we have just looked into the third law of thermodynamics based on the definition of entropy. Now we'll look into Maxwell's relations, that is to relate entropy with other thermodynamic parameters, and thereby we'll be discussing on what is the law of increase of entropy in terms of reversible system and an irreversible system. And lastly, we'll be restating the second law of thermodynamics in terms of entropy. So, as we have discussed the third law of thermodynamics as suggested by Nernst, that entropy change of a transformation between phases will be approaching zero whenever the temperature will approach zero. That means there is no change in entropy when the system is stable. Even if there is a transformation that happens at a transition temperature at 0 Kelvin, there won't be any appreciable change in entropy. So this led to stating the third law of thermodynamics, which means that for every element, if it is in the stable state, then the entropy can be taken to be 0. And then every substance will have a positive entropy for all the temperature except at T equal to 0. As T equal to 0, the entropy will become 0. For all at the higher temperature, the entropy will be increasing or positive 1. So entropy becomes 0 for all perfectly ordered state of condensed matter. It has to be pointed out that it is excluded for disordered material. We are considering the ordered state of condensed matter, which happens at 0 Kelvin. So there are some relations, 4 relations which quantify the entropy changes which are not directly measurable otherwise in terms of measurable quantities like temperature, volume and pressure. So let us consider how the entropy is related by taking the concept of internal energy. As you know, for internal energy, if the work is done is due to the change in volume, you can represent the internal energy as d bar q minus PdV. Work is done by the system, so it is minus PdV. And as per the definition of entropy, d bar q is given by TdS. So you can replace that minus PdV. So from the representation, you can see that the internal energy has been expressed or expanded in terms of a function of a change in entropy as well as a change in volume. So which implies the internal energy will be a function of S, entropy and volume. So now you can make use of the expansion, the total derivative u can be expanded as which all dependent variables are there, you will be representing partial derivatives of those. So u is dependent on S, which means dou u by dou S, keeping the other variable constant, volume constant, into the change in the dependent parameter, that is ds, plus the second dependent variable is volume. So changing internal energy with respect to volume, keeping entropy constant into the change in volume. So that is how we represent a function which depends upon any of the variables. And you know the internal energy is a analytic function. So which means dou u by dou s and dou u by dou v are continuous. Those partial derivatives are continuous function. So you can write, if it is a continuous function, if I vary dou u by dou s and then dou by the variation with respect to volume, it would be the same if I vary internal energy with respect to volume first and then by entropy. That is the property of a continuous nature of a partial derivative. So making use of that, you can see dou u by dou s. What is from this relation, if I change du with respect to ds, keeping volume constant, I will get temperature as a coefficient. So instead of dou u by dou s, I can represent it as temperature. And you have one more differential involved, that is dou by dou v. Okay, so it is, in the LHS it become dou by dou v of temperature at constant entropy. Similarly, in the expression for du, if I keep entropy constant and check only the change of volume, then it will be getting the coefficient of that term, that is minus pressure. So dou by dou s of minus p will be obtained, or in general you can write minus of dou p by dou s at constant volume. So that is the first relation. I can measure the change in pressure with respect to entropy by just analyzing what is the change in temperature with respect to volume with a constant entropy. And a negative sign is also involved. And the second relation can be obtained by another parameter which is called Helmholtz free energy F. So in Helmholtz free energy, F is defined as internal energy minus Ts. It is also a function of state, and from the expression, if I differentiate it, I will be getting it as dF is equal to du minus, this is a product function, so I need to get two terms, that is T into ds minus dt into s into dt. So that is how I get the differential. And you already know du is given by d bar q minus p dv, or you have just seen it as t ds minus p dv. So instead of t ds minus p dv, instead of du, I can enter t ds minus p dv. So it becomes cancelled out, TDS and minus TDS. So finally you have minus SDT minus PdV, and from the earlier experience you can write it as dF is obtained as a function of temperature and volume. Okay, so now I can write it in terms of a total derivative can be represented in terms of partial derivatives of the dependent variable. So that is dou f by dou t at constant volume into the change in temperature, that is dt, plus dou f by dou v at constant temperature into the change in volume, that is dv. Here also, because it is represented as a function of state, dou f by dou t and dou f by dou v are partial derivatives, are continuous, and hence you can again write, I can take the variation of f with respect to temperature first and then vary it with respect to volume, or it would be the same as if I take f, the variation of f with respect to volume followed by variation with respect to temperature. Both will be the same. And from checking the first equation for df, what is dou f by dou t? That is change in f with respect to temperature alone, keeping volume constant. Then I will get the coefficient of dt term, that is minus s. Similarly, dou f by dou volume will be the coefficient of dv, that is minus p. So substituting that, I will get it as dou by dou v of minus s is equal to dou by dou t of minus p. So in both the sides, negative sign will cancel out. So finally we have the change in entropy with respect to the volume can be determined as by just taking the change in pressure with respect to the temperature at constant volume. So we can determine how much is the change in entropy with respect to change in volume just by checking the amount of change in pressure with respect to temperature at constant volume. So that is the second relation. And for the third relation, I can use enthalpy H, and we have already seen that enthalpy dH is given by TdS plus VdP, or it is d bar Q plus VdP, which is enthalpy. So from that we can see that it is a function of ds, a change in, dependent on change in entropy as well as change in pressure. So the dependent variables can be assumed from here, which is h as a function of s and pressure. And now you can make use of the concept of total derivative for h in terms of the dependent variables. So it would be dou h by dou s at constant pressure into the change in entropy, and dou h by dou p at constant entropy into dp. And again, you can see that enthalpy is a function of state. So I can see that I can make use of the continuous nature of partial derivative. So if I vary dou h by dou s first, followed by the variation with respect to pressure, it would be the same if I vary dou h by dou p first and then do the variation with respect to entropy. Now from the first relation, we can see what is the change in enthalpy with respect to entropy at constant pressure. It would be the coefficient of TdS. What is that? T. And similarly, dou h by dou p will be coefficient of that term, which is volume. So I'll be getting dou by dou p of temperature is equal to dou by dou s of volume at constant pressure. Okay, so that is the third relation. And the last relation can be obtained from Gibbs free energy, which is defined as G is equal to H minus Ts. So writing down the differential for the given equation, we have dG is equal to dH minus TdS minus S into dt. That is applying the product rule for the second term. And you already know what is dH. It is d bar Q plus VdP minus TdS minus STT. And what is d bar Q? It is TdS. So TdS and this TdS will cancel off. So remaining we have VdP minus SDT, or minus STT plus VdP, which means G is the variation in G is due to the variation in temperature or variation in pressure. That means we can assume G as a function of temperature and pressure. Now you can apply total derivative for this. The total derivative dG will be then dou G by dou T at constant pressure into the amount change in temperature plus dou G by dou P at constant temperature into the amount which is changed, dP. Now G is also a analytic function, and hence we can apply the concept that the partial derivatives are continuous, so the order is immaterial. So if I vary G with respect to temperature first, followed by with respect to pressure, it would be the same if I do G with respect to pressure first and then vary with respect to temperature. Both of them will be giving the same answer. Now you know dou G by dou T from the first relation for dG. It is the change in temperature. With respect to the change in temperature, it is minus S, and with respect to change in pressure, it is volume V. So it would be dou by dou P of minus S is equal to dou by dou T of volume. Okay, so you have the last relation. You can measure or determine the change in entropy with respect to the pressure by just analyzing the negative of the change in volume with respect to temperature at constant pressure. So these four relations help us to quantify the change in entropy in terms of the measurable quantities, temperature, volume and pressure. So we have U from the expression for internal energy, which is Q plus work, heat plus work done, and from the expression for Helmholtz free energy and enthalpy and Gibbs energy, we can obtain four relations. For the first one, we have the variation of pressure with respect to entropy can be measured as at constant volume is given by minus of the variation of temperature with respect to volume that is happening at constant entropy. Now, if you want to measure what is a change in entropy with respect to volume at constant temperature, it is given by just to take the change in pressure with respect to temperature at constant volume. That is obtained from Helmholtz free energy. Now, from enthalpy, we have the relation the change in volume with respect to entropy at constant pressure will be same as the change in temperature with respect to pressure at constant entropy with a negative sign. And for change in entropy with pressure at constant temperature will be same as just to measure the change in volume with respect to temperature at constant pressure with a negative sign. So these are the four Maxwell's relations which help us to find out the entropy changes with respect to the measurable parameters, pressure, volume and temperature. So that is the relevance of Maxwell's relations. Now let us see what you mean by law of increase of entropy. For that, let us consider a composite engine of an irreversible engine feeding the Carnot engine working backward. Okay, so you have two reservoirs, hotter reservoir and a colder reservoir represented by blue line, and heat is taken from the hotter reservoir and work is given to the Carnot engine and some heat is given to the cold. And based on the work done, heat is taken from the cold reservoir and given to the hot reservoir. So, and you already know the efficiency of Carnot cycle is greater than an irreversible engine. So, you can represent the efficiency of irreversible engine eta I is greater than eta R. So that means here it should be a negative symbol. It should be like this. Efficiency of reversible engine must be greater. So you can write it as 1 minus Q2 by Q1 must be less than 1 minus Q2 prime by minus Q1 prime. How do you write that? Efficiency is written as 1 minus the heat to the cold reservoir divided by heat from the hotter reservoir. So it is minus Q2 because it is given. Okay, I think I have written in the wrong way. So it is, this is the expression for eta R and this is the expression for eta I. So then it is correct form. Okay, the only difference is here it should be reversible case and here it should be irreversible case, which is I. Okay, so it is 1 minus from the colder, it is given by minus Q2 divided by Q1 will be greater than 1 minus Q2 prime, that is colder, by hotter. Colder is given by Q2 prime divided by minus Q1 prime. Okay, so here you have minus 1 minus and 1 minus can be cancelled. So it is minus Q2 by Q1 will be lesser than Q2 prime by Q1 prime because these terms are considered, 1 minus these terms are considered. Okay, so if I have A minus B greater than A minus C, which implies the B is a very smaller quantity than the C. Then only this difference will be greater. So that is what is written here. The B is represented less than C. So the B value is minus Q2 by Q1 and C value is Q2 prime by minus Q1 prime. So hope that is clear for you. So you have the heat flow in the Carnot cycle. We have already obtained that the ratio of heat flow will be same as the ratio of the temperature. So minus Q2 by Q1 is equal to T2 by T2 is the temperature of the cold reservoir, T1 is the temperature of the hot reservoir, T2 by T1. So you can write it as Q2 prime. Instead of minus Q2 and by Q1, I can represent it as T2 by T1. So T2 by T1 is less than Q2 prime by Q1 prime minus Q1 prime, or Q2 prime by Q1 prime is greater than T2 by T1. Now I am going to split up the entire cycle into lots of tiny cycle considering a small heat flow as part of it. So you have two parts available. One is from A to B, which is using a reversible engine, and other is using B to A using Carnot engine. And we have the expression as we are representing a very small heat flow. So instead of Q2 prime, I have D bar Q2 prime divided by D bar Q1 prime is greater than T2 by T1 from the previous expression. And by just rearranging it, I have minus D bar Q2 prime divided by T2 is taken to the RHS. T2 is greater than D bar Q1 prime by T1. And by taking this to the RHS, I have 0 is greater than D bar Q1 prime by T1 plus D bar Q2 prime by T2 for one tiny cycle. So adding together all the tiny cycle, that is for a single tiny cycle. Now considering all tiny cycle, to make up the total cycle, it would be integrating D bar Q for the reversible case divided by Ti. Corresponding temperature will be less than 0. This was 0 greater, which means less than 0. So that is an important parameter for a system involving irreversible engine. The total heat divided by temperature, corresponding temperature will be less than 0. So the splitting up the cycle into two parts, the reversible part as AB and reversible part as BA, I can represent it as the LHS can be splitted up. So it is integral A to B D bar Q irreversible path divided by temperature for the path 1, which is A to B, plus from B to A, that is integral B to A, D bar Q is a reversible one divided by temperature for the path 2 will be less than 0. Or just by rearranging, integrating A to B, D bar Q reversible by temperature for the path 1 is less than that for the reversible case. So integral along the reversible path is familiar. For a reversible path, this integral can be replaced with the definition for entropy, rather entropy difference, S of BA. So the expression will become integral A to B D bar Q irreversible by temperature will be less than, instead of this expression I can write entropy of BA. So if A and B are very close together, then S can be replaced at very small change in entropy, delta S. So inequality will become delta Q irreversible by temperature will be less than delta S, where delta Q is also a very small change amount of heat that is added, represented as integral A to B D bar Q irreversible by temperature. So that inequality where the heat added divided by temperature is less than the change in entropy for the system is called Clausius inequality. That means for an irreversible process, the increase in entropy is greater than delta Q. Always there is an increase in entropy greater than the amount of heat that is supplied. Okay, so that is the essence of law of increase of entropy, which is given by Clausius inequality. For an irreversible system, the change in entropy will be always greater than the amount of heat that is supplied to the system. So if I say there is no heat supply, if it is a thermally isolated system, then this factor will be 0. Then what would be the expression? It would be the change in entropy will be greater than 0. So even if it is an isolated system, the system will try to increase the entropy. Okay, so that is the essence of law of increase in entropy. If at all the system is in thermally isolated system, the entropy will be always positive change. So it is a direct consequence of second law of thermodynamics. That means the heat transfer will happen only from hotter region to the colder region. That is why we have obtained the Carnot engine as a most efficient one. That is why the efficiency has been written, expression for efficiency, and from that we have obtained the Clausius inequality. That is why it is mentioned as it is a direct consequence of second law of thermodynamics. So the law of increase in entropy states that for an irreversible process and also for the reversible process. For the irreversible process, the increase or the change in entropy will be always greater than the total heat supplied to the system divided by temperature. For a thermally isolated system, it would be 0, so it is always positive. So all changes in a thermally isolated system lead to an increase in entropy. While for a reversible process, delta is equal to the heat supplied by temperature. So if it is a thermally isolated system, the change would be 0. The entropy will remain unchanged if the process is reversible. So these are the two essence of law of increase in entropy. So we need to consider whether the process is an irreversible process or a reversible process to check. And we can see that if it is an irreversible process, if there is a system with an increase in entropy, it shows that it is a irreversible process happening in that system. If you have a system with no change in entropy, which implies that reversible process is happening in the system. So in the reverse way, in the inverted way also we can make use of the concept of law of increase in entropy. So whenever a thermally isolated system is approaching equilibrium, which is an irreversible process, equilibrium state is a stable case which will not be reverted. That means it is an irreversible process. So the entropy must increase. The final equilibrium configuration will be the one with maximum entropy. So that is another statement of law of increase in entropy, that the system always try to have maximum entropy whenever it try to reach for the equilibrium state. Okay, so the second law of thermodynamics, which has been defined in terms of transfer of heat by Kelvin and Planck, Clausius, and by Kelvin and Planck, it was remarked that it is impossible to extract an amount of heat from a hot reservoir and use it for all work. Some has to be exhausted to the cold reservoir. While the Clausius has pointed out that it is not possible for heat to flow from colder body to a warmer body without the help of any work. So if the reversible process occurs, there is no net change in entropy, and in an irreversible process, entropy will always increase. So the change in entropy is positive for a irreversible system. Total entropy of the universe will continually increase. It will never decrease. That is the statement of second law of thermodynamics in terms of entropy. It's a consequence of all these statements. Okay, so the second law of thermodynamic can be stated in terms of entropy as for a reversible process, there is no net change in entropy. And if it is an irreversible process, entropy will go on increasing. So the total entropy of the universe will always increase. Now, many processes are irreversible process. You know, whenever we add ice to a lemonade, ice will just melt off. Will it come back to the normal ice state? No, unless it is placed in a refrigerator, in a freezer, it won't come back. So it is a irreversible process. Okay, so an irreversible process increases the level of disorder. Okay, it was in a solid state. Ice was in a solid state, which means in a compact packing. Once it melts down, it will come to the molecules are more in a disordered state, isn't it? So you can see as the state for the irreversible process, it will always have a transition from ordered state to the disordered state, which means an entropy will, there is a change in entropy. So it indicates that which way the time goes. So if you have two uh, lemonades, one with more ice and other with the same amount of ice, but some has been melted. So if you are given such two glasses, how do you identify which has happened faster, earlier? എങ്ങനെയാണ്? You just have to check which has more disorder. So the more disorder or more entropy should have happened earlier. So that is the usual, the natural time flow. Always increases the disorder. രണ്ട് lemonade ഉണ്ട്, and if that has, one is having melted ice and other is having just formed ice, just an ice form. If you are not aware which one has been placed or first, then it can be seen that one is in a liquid form, which means it has been melted. അപ്പോൾ അതാണ് കൂടുതലും ആദ്യമേ പുറത്തെടുത്ത് വെച്ചിട്ടുണ്ടാവുക. So similarly, you can see that since we can use the entropy as a measure of time. So if there are more entropy for a system than the other, how do you know more entropy? More disorder is there, which means it has happened first. So since entropy gives information about the evolution of a system with time, it is said to give us the direction of time's arrow. Okay, so you can know in which way the time has proceeded by just checking which is having more entropy or which is having more disorder. So if the snapshot of a system at two different times shows one state which is more disordered, then it could be implied that this state came later in time. Okay, so if you have two photograph of a same system, one is having more disorder and other is having less disorder, which it implies the disordered state picture has happened earlier. Disordered state started earlier, that means it has happened later in time. Okay, so the disordered state will be the just completed state, just time evolved state. Okay, so for an isolated system, the natural course of events take the system to a more disordered state. But naturally എല്ലാം നടക്കുന്നത് how you can increase the disorder. Okay, for any system, it always try to increase the disorderness, which means it tries to increase entropy in the system. So certain things happens in one direction and not the other, and this is called arrow of time, and it encompasses every area of science. So that explains why the ice is getting melted into water. It happens in one way if we place it outside the refrigerator. Why? Because it is the state in which we have more disorder. When it converts from solid to liquid, it will have more disorder. That is why the nature prefers to do in that particular direction. Okay, so that explains why the heat flows from hotter body to the colder body alone, because that's a way the disorder can be increased or the entropy can be increased. So we can say there is an arrow of time. Arrow of time means there is a single direction always the nature prefers to have, which means it is the direction which more disorder is happening. Okay, so we always have many questions why it has happened in only one way alone. Why? Because the nature prefers to have more disorder so that the entropy can be increased. So the thermodynamic arrow of time can be taken as entropy. Entropy can be considered as a thermodynamic arrow of time. ഒരു സിസ്റ്റം തന്നിട്ടുണ്ട്, അതിൻ്റെ ടൈം എവല്യൂഷൻ മനസ്സിലാക്കണമെന്നുണ്ടെങ്കിൽ you just have to check the entropy, the change in entropy. If it has increased, that means the time has elapsed. Okay. So it is a measurement. The thermodynamic arrow of time can be analyzed by measuring the disorder within a system. So entropy also describes how much energy is not available to do work. So more disorder means it has been displaced a lot, which means that much energy has been used up for displacing, for increasing the disorder. So those energy is not available to do any useful work. So the more disordered a system, higher the entropy, the less of a system the energy is available to do the work. Okay, because more disorder means that much lesser energy is now available for to do any work. So if you have two systems, if the particle represent gas molecules at normal temperature inside a closed container, which of the illustrated configurations came first? Okay, you have given two snapshots of particles inside a container at normal temperature. So you are asked which of these has formed first. So you can see that in the right picture it is having more ordered state, and in the left picture you can see it is in a disordered state. So which would have happened earlier? The ordered state has happened earlier and the disordered has just happened. So you can know which is the time flow. This is the first one, and the second one has happened is the disordered. Similarly, if you toss the bricks of a truck, if you are just making the bricks tossing off to the ground, can you expect it to form in an ordered state? Which kind of pile of bricks would you more likely produce? Is it an ordered form the tossing would happen? Then it would have been better, no? No, it is happening in a disordered state because it is the most probable state than the ordered state. Okay, so for an isolated system, entropy always increases or remains the same. So if you compare the state of different entropy, the one with greater entropy will be later in time. Okay, it has been in an ordered form in the truck, and when it is been tossed off a truck, it will be in a this kind of arrangement, disordered arrangement. So that ends the chapter 2. We have seen the entropy as a function of state, and see the important concept of Carnot cycle and composite engine, and define the entropy and define the third law of thermodynamics, and we have seen how to measure entropy by measuring the non-parameters like measurable parameters like temperature, pressure and volume of the system, and what I meant by law of increase of entropy in terms of a reversible system and for reversible system, and we have restated the second law of thermodynamics in terms of entropy. So hope you have understood. Thank you.